Greetings. Welcome to Machine vs Mathematics channel. You have a discrete time system. Say it has both zeros and poles. If the poles of the discrete time system lies inside the unit circle, that discrete time system is a stable system. If any poles are lying on the unit circle, now system would be marginal stable. Okay, if poles are lying outside the unit circle, system is unstable. Now in that scenario, you are given a system like this. Yeah, so this is input, here we have input and output, and system is just defined like this. Now in that scenario, GATE Electrical 2007, he asked for 2 marks. Now he is asking us to find the value of K so that system is stable. Yeah, and the K is in the feedback path. Yeah, the K is in the feedback path and you have a positive feedback. Okay, and now you know how to write its transfer function, because here in this forward path you have z of z. Now its impulse response he gave us like this. See, he gave us something like z of n, and g of n is having life for n equal to 1 and 2. Other than n equal to 1 and 2, g of n has no life. So we can have g of n from this, and from that g of n we can apply z transform to find g of z, and that we apply in this transfer function. Then for what range of k, and that k we can find to get this or to solve this answer. It is very simple to solve, there is no big deal, but it is given for 2 marks, right? Of course, this must be given for 2 marks. See, now what is given to you? Now the impulse response of g of z, the impulse response of z of z is given to you like this: z of 0 equal to 0, and g of 1 equal to 1, g of 2 also equal to 1, remaining components g of 3, g of 4, g of 5, whatever, so on, it is 0. So therefore, what is given to you is this. This is, say, my g of n. Okay, this is my g of n, and g of 0, so z of 0 equal to 0, so I have 0 here, and I have 1, 2, 3, 4, so on. Okay, now what is g of 1? G of 1 is given to you as 1, so this is 1, and g of 2 also given as 1, and g of 3, g of 4, g of 5, so on, they are zeros. Okay, so they are zeros. So now you have g of n defined like this. So we can say that g of n we can write, because see, any discrete time sequence can be expressed as linear combination of weighted shifted impulse functions. Yes or not? So in that situation we can write this g of n as follows. See, I have sample whose value is 1, sample 1 at n equal to 1. That means delta n minus 1. Now I have again sample value 1 plus this sample value 1. Okay, and this fellow is existing at n equal to 2. That is delta n minus 2. And for remaining n, 3, 4, 5, so on, 0, minus 2, so on, you have no life, or g of n is 0 for that. So therefore g of n is this. Now you can apply z transform. So if you apply z transform, what are we going to get? It is very simple, you see. So let me apply z transform. G of z is equal to, so you get z power minus 1 multiplied by 1 plus z power minus 2 again multiplied by 1. How come? Because you know very well like this. Say x of n is a discrete time domain signal or sequence whose z transform is given x of z. Now let me take x of n as some delta of n. Now if you take its z transform, you know it is 1, x of z equal to 1. Okay, so in this case ROC is entire z plane. Now you see, now if I take delta of some n minus, say, n sub 0, then its z transform is what? Z power minus n naught multiplied by x of z. X of z equal to what here? If x of n is delta n, x of z equal to 1. So this fellow is now 1. Yeah, because we know very well x of n minus n naught is nothing but z power minus n naught multiplied by x of z. So z power minus n naught multiplied by x of z equal to 1 and x of n equal to delta n. So therefore we have like this. Okay. So once you have this g of z, so once we have this g of z, now what can we decide? Because if you're able to find this transfer function, say I can take it down like this, closed loop transfer function of this system, yeah, is say output transform by input transform. See, output transform by input transform. So you will get like this, g of z over 1 minus k g of z. Yes or not? That's it. It's very easy. I hope you know how to get this one. As it is positive feedback, we obtained here 1 minus k multiplied by. If it is negative feedback, you would get 1 plus k multiplied by z of z. Alright, so now we have to, of course we have this, and now also we have done with g of z, and now we should be able to find this k such that this system must be stable. Okay, so now you have set everything. Now let us knuckle down to find the range of k, or at least the value of k. Okay, so let me say my transfer function. Let me take t of z equal to, this is say z of z over 1 minus k g of z. So we have revisited our equation again. So we obtained like this. This is what we have already. Okay. Now what is g of z? So z of z we obtained. So t of z equal to z power minus 1 plus z power minus 1 plus z power minus 2. Okay, so z power minus 1 plus z power minus 2 is our g of z divided by 1 minus k multiplied by z power minus 1 plus z power minus 2. Yeah, so our g of z is this, z power minus 1 plus z power minus 2. Alright, so we plugged in things here, so we have this one. Yeah, now we know very well system will be stable if all the poles lie inside the unit circle, right? So inside the unit circle. Okay, so my z plane, as z is a complex variable, so we have a complex plane. This is real z, and now you have imaginary z. So whatever, if I take a unit circle means a circle whose radius is 1. Alright, so if all my poles lie inside this unit circle, whatever system I have, that must be a stable system. Okay, so as of now, how many poles we have? As we have z power minus 2 in this denominator, so this fellow will accommodate poles, right? So we have 2 poles, so whatever poles I have, that must be inside this. If I have any pole on the unit circle, system is marginal stable. See, he is saying stable, but he did not really mention whether it is marginal stable or perfectly stable. So our options may suit marginal stable or completely stable. So now we will try to find things out. Don't worry. So I'll go for it first. We are saying that all the poles lie inside the unit circle. So that inside the unit circle, I will take it as like this, less than 1. Okay, so t of whatever we have, the poles, we have like this. So I'll take this one. Yeah, this fellow will decide my poles, right? That means you see, I have 1 minus k z power minus 1 minus k z power minus 2. So location of poles, how do I do this? See, this one, if you have real problem with working out with z power negative, if exponents are negative, if you find exponents are negative quantity, you can convert exponents as positive, just multiplying and divide by the highest order like this. For example, you see, before I go for it, let me put down this thing is very simple. Okay, so now you have t of z. All right, so let me multiply and divide by z squared. So now what you get? So we get this is what z, and this is plus 1. So you have a single zero we have now. Other zero must be at infinity because you have couple of poles. In every system there must be equal number of zeros and poles. Yeah, sometimes you could find more number of zeros than poles, sometimes you could find more number of poles than zeros. See, if you have more number of poles than zeros, the remaining zeros we would assume at k equal to some infinity. That is a very useful process. Now if you have more number of zeros when compared to these poles, then can we imagine poles at infinity? Like we are assuming remaining zeros at k equal to infinity. In the same way, can we assume poles at infinity also? Yeah, you have some finite poles. See, for example, like this. I have some m number of zeros. What I'm saying is this, m zeros, and I have n poles. Yeah, and we are very familiar with working out with these conditions for n greater than m. Now if you have m greater than n, that means number of zeros are dominating when compared to number of poles. In this scenario, can we introduce the remaining means how many? Can we introduce that, or can we assume the remaining m minus n number of poles at infinity? Yeah, please, if you know the answer, please share your thoughts in our comment section below for this. This is very interesting and important to understand. Okay, so anyways, back to this story again. So we are multiplying and dividing by z squared to make these exponents positive. So what are exponents we have? We want to make them positive here. All right, everywhere, both here and here. So we have this, and now this is z squared minus kz minus k. Okay, so now I can take this. Now I can take this fellow to find the poles of this system. Now he's saying that system must be stable. So all poles lie inside the unit circle. So therefore, how do I do this? Let me find for z. Now if z is, I can find roots for this. Minus plus or minus, say, b square 4ac over 2a. This 2 multiplied by 1, it is 2. So this fellow must be less than 1. That's it. Yeah. So how many poles I'm going to get here? I have 2 poles. If these 2 poles are less than 1, yes, yeah, that means we are stable. And for what k we are getting less than 1, that we have to check now. Okay, so let me put things down like this: k plus or minus k square plus 4k. Okay, 4k, say it is less than 2. All right, so let me square on both sides. Let me take for now, I will take any one pole and I can make it on k minus things ladder. Let me take only one case for now. So we have k plus k square plus 4k This is less than 2. This is what we have. Alright. So now k square plus 4k, k square plus 4k is less than 2 minus k. So you square on both sides. So k square plus 4k must be less than k square plus 4 minus 4k. Okay, so we can rule out these two fellows, and now you have 4k and here we have negative 4k, so 8k less than 4. So 8k less than 4. Now k is what? Less than half. So k is less than less than half. Now you please tell me. So now if you want to include or if you want to consider poles inside the unit circle, then k must be less than half. Okay, k must be less than half. So which option do you think is correct? I have negative 1. Of course, negative 1 is less than half. So this is correct. Negative 1 less than half, of course, correct. Negative half less than half, correct. Negative half again. See, that means first quantity everywhere it is satisfying. Now see, for example, this one, half. Yeah, you see, this 1 is greater than half, so I can remove this b. Again, 1 is greater than, remove this. This 2 is greater than half, remove this. The only possibility is this one. Yeah, I have here again half. So k must be less than half. Yeah, see, we obtain k less than half, but here I have again half. So we can include also unit circle if that becomes a marginal stable stuff. But the only thing in this case, if you compare these 4 options, only first option is feasible, right? Because this fellow, the 1, 2, whatever, they are greater than half. So therefore we can eliminate them. So somehow we can come to this conclusion. So this fellow will win the race. The answer is what? Minus 1 comma half. Minus 1 comma half is its answer. So it's very simple, right? There is no big deal. Just we need to see. Just we need to understand this. GATE examination has, a 5 category of questions: recall based questions, recall based or formula based questions, application based questions, comprehensive based questions, analysis based questions, and synthesis based questions. So whenever GATE fellow asks a question or set of questions, he will try to see to that questions come under these 5 categories. So accordingly, you have to practice your GATE examination. Definitely you can crack things. Okay, so that's it for today. Thank you and bye.